We'll begin now starting to talk about how to go through other types of diagnostic procedures. The first of which is figuring out whether or not you have any outliers or influential observations in your data. Remember that in order to use these diagnostic tools in R, you need to first load the CAR library. And again, you're going to be looking for pretty much the exact same kind of things that you were looking for before in the case of OLS, where you're interested in the studentized residuals, hat values, the Cook's distance, and outlier test as well. So here, I'm basically just looking using the VIF as well as these are actually the hat values. So these are pretty small hat values, if you remember correctly. And here, this is basically telling us that no studentized residuals have a large either studentized residual or unadjusted studentized residual. And those p-value, the p-value is quite large to begin with. It wouldn't meet the critical threshold of 0.05 to begin with. And the corrected Bonferroni p-value is larger than 0.05. Let's now just take a look graphically at whether or not there are any outliers or observations that are giving undue influence on our estimated coefficients. And looking at the bubble plot here of studentized residuals versus hat values, and those Cook's distances, right, are the width of the circles, we can see that there really aren't any observations that seem to be providing any undue influence on our estimates. Now, when we're just talking in general about the goodness of fit of the model, we do want to look at how well our model is fitting for different values of x along a covariate of interest. But this is kind of problematic, at least transferring the tools that we used in ordinary least squares moving to the logit, just because our response variable, right, is 0 or 1. And so in order to correct for that, we're going to do an HL goodness of fit test. And in order to kind of show you exactly what's going on here, we're going to return to our original example of having coronary heart disease. So again, remember, you have some fitted value, which is the probability of having CHD in the first place, right? Now, the logistic regression is going to give you, or it's going to estimate the predicted probability, right? The fitted value of having CHD for every value of X, or age in this instance. Now, what we want to do is check to see whether or not for each of those values of X, our model fit is very good. So we're going to partition the observations into different groups. So from 20 to 29, 30 to 39, and we're going to get an estimated or predicted probability of having CHD for each of those groups. And in each of those, we are not going to consider the other fitted values. So this is not exactly like performing or constructing our fitted regression line along the logistic function, right? Where it's a smooth curve. We're kind of subsetting elements here. So the predicted probabilities and the confidence intervals for each of these subgroups is only based on the observations in that subgroup. And again, we're going to compare that to the freely fit, or the fitted values that we get along that logistic function normally, without using a conditional subsample of groups. So this is to kind of show you visually what that's going to look like. So again, we have like 10 different groups subsetted by age, and we're calculating the predicted likelihood of CHD for that subgroup only. And again, those confidence intervals are 95% confidence intervals around the predicted subgroup value or propensity of having CHD. Now, what's interesting is that we can do this also for our judge progressivism example, in which case we can use a chi-square test statistic to see whether or not we have sufficient fit. So again, since we're using proof by contradiction, our null is going to be that there is sufficient fit, and our alternative is going to be that the fit is not sufficient. So again, we can compare, right, the normal fitted values along the logistic function to those that we get from the HL test, and we're seeing whether or not those are different from each other, just as kind of a background reminder of what's going on here. So we run our HL test in R. Again, here is our outcome. Here are our fitted values from our additive model. So when we actually look at this, we see that we get a p-value that is quite large. So we cannot reject the null that the logistic regression describes the data reasonably well, which is a good thing. That's what we're looking for.